All right, everyone. Good afternoon. The topic of today's class is a sort of continuation to what we did last class. Last class, we learned how to decide whether or not two graphs are isomorphic as long as they have simple eigenvalues. And we achieved that by showing how to associate in a canonical way the vertices of a graph with simple eigenvalues to the eigenvalues of the graph, right? So to very briefly, oops, I just disappeared. Yeah, so to just briefly remind you, what did we do? We started with the one eigenvector matrix of the graph, and the assumption was that these eigenvectors corresponded to the eigenvalues of the graph, say in decreasing order, right? We are assuming the graph has simple eigenvalues, therefore all eigenvalues are different. So in the case of P4, which was the running example of last class, we had the eigenvalues up here, and each one of those corresponded to each one of these columns, as long as A is roughly 0.6, B is roughly 0.37. And then the first thing that we did was to recognize that there are ways of selecting one entry in each row and column so that all of these entries are non-zero. And amongst all such ways, we pick those for which there's a sequence of squares starting from the first column to the last was lexicographically maximal. So in this particular example, we had 4 ways of doing that, each one corresponding to one way of picking the entry A, which is larger than B, 1 in each row and column. So this was one such an example. And because we will be taking squares here, we could also take the negative. So negative A was also valid. And so this is another such example. There are four ways of doing that in this particular graph. It's always going to correspond to the sequence A squared, A squared, A squared, A squared. These 4 ways are described here. And then we had a discussion on why we can always find at least one of these, meaning why there is always at least one choice of an entry in each row and column, all of those different than 0, right? So in principle, it could be, who knows, that in a eigenvector matrix, it was impossible to select one entry in each row and column equal to 0. However, we saw that this is not the case because this matrix is invertible. Then this theorem guaranteed that there is always one such way. Amongst all of those, we picked the lexicographically maximal. Then we reordered rows according to the lexicographic ordering of rows. Then we reordered the columns, and not reordered, but we picked the one with the whose columns were lexicographically bigger amongst all of those. And then we argued that this is a canonical choice, meaning that no matter which eigenvector matrix you start, you will, as long as this is normalized, you will always end up with the same eigenvector matrix, and this was what we call a canonical star basis for this case. All right? So we had this theorem 2.5 showing that two graphs are isomorphic if and only if two graphs with simple eigenvalues are isomorphic if and only if they have the same eigenvalues and they admit the same canonical star basis. And then we spent the second half of the class discussing how to actually compute this canonical star basis efficiently, because in this description that we had during class, there was a step here, that involved computing a bunch of permutations and selecting amongst all of them the lexicographically largest. If you decide to do this the naive way, by actually computing all of these permutations, looking at all of them and picking the lexicographically maximal, that wouldn't be efficient at all. So we learned how to actually, in a sort of like on demand, find this permutation that will eventually already be the canonically correspond to the canonical star basis. Right, so this was the second half of class, and this is, in a sense, the graph isomorphism algorithm that allows one to decide whether or not your graphs with simple eigenvalues are isomorphic. Now, fortunately, this algorithm, fortunately, this theorem is quite useful because most graphs have simple eigenvalues. So this proves that most graphs, you can decide graph isomorphism for most graphs in polynomial time. Now, this is not the most efficient algorithm, but is certainly, and I say this from experience, this is certainly the most simple to understand. It's not the most efficient because you will have to compute several perfect matching, maximum perfect matching algorithms to achieve this, and these are not super efficient. However, they're all solvable in polynomial time. So this is not the most efficient. There is a way you can bypass this and sort, but it's too complicated. And yes. Now, this pretty much settled the problem of deciding whether or not your graphs with simple eigenvalues are isomorphic. How about other graphs? How about graphs in which one eigenspace has possibly a larger dimension? What can you do? All right, so this is the topic of today's class. We will talk about star bases and larger multiplicities. All right. So, why exactly the problem becomes much more complicated? Because when you have simple eigenvalues, there are essentially, well, there are only two eigenvectors per eigenspace with a norm 1. So if you normalize your vectors, there are only two choices. And this is good. If there are only one choice, graph isomorphism would be trivial. Because there are two choices, you have to somehow test them. Of course, you're not going to test all possibilities, otherwise that would be exponential. But what we did last class was basically a way of, well, dealing with this problem. Now, if you have an eigenspace with multiplicity larger than 1, there are now infinitely many possible bases for that eigenspace, right? Because now you can pick an eigenvector and it's orthogonal within the eigenspace, but you can take another linear combination of those and they're orthogonal and you have a different basis. There are infinitely many bases to any subspace, right? Even if you enforce that your basis is normalized, infinitely many bases for a subspace with dimension larger than 2, right? So there is no natural immediate generalization to lemma 2.1. Lemma 2.1 is the lemma we actually saw in the other class. Lemma 2.1, oops, what am I doing? Shit, that's not true up here. Lemma 2.1 was the lemma that said that every isomorphism of a graph between two graphs with simple eigenvalues corresponds to a diagonal matrix whose entries are plus and minus 1. And this was quite important to the proof that the canonical star basis thing actually worked. So there is no analogous to that thing, and that is a problem. So with this in mind, the topic of today's class is to discuss basically how you can find canonical bases for each eigenspace. Okay? So the first problem, or at least the first goal, is to prove or to realize, or at least to reduce the problem to a finite number of possibilities. So recall before, again, each eigenspace, we had 2 possible vectors generating. Now we have infinitely many possible bases for each eigenspace, but let's try to at least canonically reduce this number of possibilities to a finite number. So this is the first goal, all right? So this will be, in today's class, our notation for the spectral decomposition of the adjacency matrix. So I will be assuming A is n by n, but I have m distinct eigenvalues. They are indexed from 1 to m. The eigenvalues will be denoted by theta r. The projectors onto the eigenspaces will be denoted by E sub r. And then, of course, as long as m is strictly smaller than n, at least one of these eigenspaces will have a dimension larger than 1. At least one of these projectors will have rank larger than 1. Right? Now, a definition now, which is key to today's class, is that a partition of the vertex set of the graph, so I am partitioning the vertex set of the graph into as many cells as I have distinct eigenvalues. So it's not a coincidence, m is equal to m. So I am partitioning my vertex set into n sets, and m is precisely the number of distinct eigenspaces. No coincidence. Okay, this is what I want. All right. So we say that such a partition is a star partition if for all r the vectors, these vectors, so the projectors onto the rth eigenspace of the characteristic vectors of the vertices in the rth cell form a basis for that eigenspace. So imagine that m is equal to 3. All right. I'm writing the first projection. I'm writing the second projection. And I'm writing here the third projection. Right? Recall that all these rows and columns are indexed by vertices. I am also partitioning the vertices of the graph into 3 cells. So let's say that I have some vertices of the graph corresponding to this, some corresponding to this, and some corresponding to this. So this is V1, V2, and V3. And this partition will be called a star partition if this columns here, this columns here, and this columns here form a basis for the eigenspaces, the theta 1 eigenspace, theta 2 eigenspace, and theta 3 eigenspace respectively. Now, you have to remember that each one of these columns is a vector which belong to the eigenspaces. Right? So, for example, if theta 1 eigenspace has multiplicity, say, 2, then you pick a basis for it. Let's say U and V form a basis, orthonormal basis. Then E sub 1 is U transpose plus V transpose. Right? So, for example, the fourth column of E sub 1 is the fourth entry of U times U plus the fourth entry of V times V. Right? Which means that this thing is an element of the theta 1 eigenspace. Because after all, U and V form a basis, and this is a linear combination of elements in the basis. All right? Not only that, but the rank of E sub 1 is the, well, there's the rank of E sub 1 is equal to the multiplicity of theta. Multiplicity of theta 1 as an eigenspace. Why? Well, because E sub 1 is a projection matrix. It has eigenvalues 1 or 0, and the number of eigenvalues 1 correspond precisely to the number of orthogonal things here. Because after all, if I multiply E sub 1 by U, I get U. If I multiply E sub 1 by V, I get V. And if I multiply E sub 1 by W, I get 0 if W is orthogonal to U and V. So U is an eigenvector with eigenvalue 1, V is an eigenvector with eigenvalue 1, and I can complement this to a basis of the space, and all of these other guys are going to be eigenvectors with eigenvalues 0. So I can diagonalize E sub 1, and I will find a diagonal matrix with 2 1s and the rest 0. So the rank of E sub 1 is 2, is the multiplicity of the eigenvalue. Now, if the rank is 2, then there are precisely, then the space spanned by the columns, right, is has dimension 2. Okay, and I'm saying that all of these columns are linear combinations of elements in the basis. These vectors are different, so at least 2 of these linear combinations will be different. So there are, in fact, 2 columns here, which are linearly independent, of course. So I can find the basis, right, for the theta 1 eigenspace amongst the columns of E sub 1. So not only for each one of these projection matrices, the columns belong to the eigenspace, but within them, there is a basis for the eigenspace. So this is all standard elementary linear algebra, all right? Now, what I want is more special now. I want to partition the column set of all of these matrices so that simultaneously the first part gives me a basis for the first eigenspace, the second part gives me a basis for the second eigenspace, and the third part gives me a basis for the third eigenspace. Or if, well, here it looks like this, but it could have been that it's not a continuous partition, of course. So it could be that V1 is actually first, second, third columns, and the last column. V2 is all the columns in the middle, except for the one, I don't know, for the 7th and 8th column, and V3 is right there. So it could be that, of course, it's not, I mean, given the ordering of the verses here, it's not necessarily true that the parts are going to be, well, blocks like this, like I drew, but that's the picture that you should have in mind. I want to find a way of partitioning the vertex set so that each cell gives me a subset of columns in the corresponding eigenspace, and that subset is a basis for that eigenspace. Any questions?
There always exists a star partition.
Yeah, we'll get there. That's the next, that's when I scroll down, that's the next result. Oh, so this will be the next result. We will actually show that there is always a star partition, which is definitely not trivial. Definitely not trivial. The first thing to notice, though, is that a star partition for a graph with simple eigenvalues is precisely what we call a star permutation. Let me go back there. So a star permutation was a choice in this eigenvector matrix of non-zero entries in each row and column. Right? Now, what happens if I write the four, which are the four projection matrices here? So E sub 1 is this first column times itself. So it's going to be B squared, BA, BA, B squared, AB, A squared, AB, oops, sorry, AB, A squared, AB, B squared, BA, BA, B squared. So this is the first matrix. I'm simply getting this vector and multiplying by itself, right? But not like this, like this. So this is the projection onto this vector. Now, what is the second? E sub 2 is A squared, AB minus AB minus A squared, BA, B squared minus B squared minus AB. This is harder than it seems. Minus BA minus B squared, AB, and then minus A squared, AB minus AB, and A squared. Oops, like that. Yes, there's a minus here. Yes, and so on, right? So you write this is E1, E2, E3, blah blah blah, and then you also write E4. Now here it's very simple. What is all these projectors have rank 1. So a basis, so all these vectors are multiples of each other. Right? In particular, this vector here is A divided by B times the first. Right? So all these vectors are multiples of each other. All these things have rank 1. So a basis for these eigenspaces is simply a choice of a non-zero column. Now, if I pick non-zero elements here, I'm exactly doing that. So I pick the third, so I'm picking this column to be my V1. I pick the second here, so I'm picking this column to be my V2. Oops. And I'll be picking the first column here to be my V3, and I'll be picking the last column here to be my V4. So a star partition here is a partition of the vertex set into n parts. So simply a choice of the vertices, and I will associate each one to a eigenspace so that the corresponding column is non-zero, which is exactly the same thing as picking non-zero elements in each row and column here. So this is a star partition is a generalization of what I called here a star permutation. Now, to show that a star permutation existed, I expanded the determinant according to this formula, and here it's not going to be any different. So to prove that a star permutation exists. Actually, before that, there is an exercise here. Oh yeah, this exercise is actually quite important. So this is probably one of the exercises that I will recommend to you guys this next week. Okay, so it's easy, but it's important to help you grasp what's going on. So prove that the following things are equivalent. Well, this being a star partition means that, again, each one of these things will form a basis. Now, I want you to prove that you do not need to require basis in your statement. If you simply require these vectors to be linearly independent, then because you have enough of those, they kind of fit the space, and each one of those will have to form a basis. And likewise, or dually, if you require these vectors to generate each one of the eigenspaces, it cannot be that they are linearly dependent because you do not have enough of them. Okay, so prove that these three things are equivalent, requiring that E sub r, E sub a1, dot dot dot, E sub r is E sub a, I don't know, k for a1, ak belonging to VR, requiring that these things generate the theta r eigenspace is the same thing as requiring that they are linearly independent for all r, which is the same thing as requiring that they span the theta r eigenspace for all r. It's a very nice exercise. But now let's move forward. Upon assuming that you have your eigenvalues, they've been ordered from largest to smallest, we say that any partition of the vertex set is a feasible partition if at least this partition has the right size. So in order for these things to form a basis for the theta r eigenspace, it must be that I have the right number, and the right number is the dimension of the theta r eigenspace. And the dimension of the theta r eigenspace is exactly the trace of E sub r. We just discussed that a little bit ago, right? So for a given partition to be a candidate to be a star partition, at least each one of the cells must have the right size. So at least x1 must have the size of the dimension of the theta 1 eigenspace, and so on. Right? To show that any graph, and in fact this theorem is true for any symmetric matrix. But we are talking about graphs, so let's keep talking about graphs. So for any graph, there exists at least one star partition. Now, this is again, consequence of a funny way of expressing the determinant. Where are you? So this equation 2 here. Oh, I'm calling this now equation 2 in my new version of the notes. So this is equation 2. This equation is quite powerful. It's again, recall that it says that the determinant of a matrix is a sum over all permutations of the sign of the permutation times a certain product, right? Of these things. Times a certain product, right? Now, so this equation is quite powerful in the sense that I can now write the sum over something different. And what is the idea here? I am going to partition the permutations into several sets. So I have n factorial permutations, and I am going to partition those. I have some permutations here, some there, some there, some there. And how am I going to partition these things? I'm going to group the permutations according to ordered partitions of a given type, meaning all permutations are so that there is a feasible partition C1 all the way up to Cm, so that the first C1 numbers from 1 to n are mapped to C1 exactly. And so on. So what do I mean by that? I have a given permutation from 1 all the way up to n. Okay, so this is my permutation. Let's say this is 3, 4, I don't know, and then let me put a example here, like 3, 4, and 5. Let's say this is my permutation. Okay. Let's say that I have examined the eigenvalues of this graph, and I know that the dimension, I have 3 eigenvalues. And let's say that their dimensions are theta 1, dimension of theta 1 is 2, dimension of theta 2 is 1, dimension of theta 3 is 2. So I am interested in all partitions of the vertex set so that the first class has size 2, the second class has size 1, and the third class has size 2. This permutation will correspond precisely to the partition given by this. Because I'm simply coming here and doing this. Note that there are other permutations which correspond to the same partition. For example, this one. Or this one. Not a problem. What I'm doing is I am examining this partition that has the right size, 2, 1, 2, contains 3, 4 in the first, 1 in the second, 2, 5, and I'm listing all permutations which give this one. And I have a list of permutations. Now I get another partition, also of the right sizes, but with different numbers. Let's say that now I want here 2, 1, 5, 3, and 4. And I also, for this one, list all permutations. So for each correct sized partition, and I have several of those, I have a bunch of permutations that go to that partition. Is that clear? Now, so that determinantal expression, the sum over all permutations, now corresponds to a sum over all feasible partitions of a sum of all permutations in there. But magically, if you stop to think a little bit, you will see that the sum over all permutations within each feasible partition is actually giving a determinant of a block matrix. So the determinant of the matrix P is the sum over all feasible partitions of plus or minus, it's not important, the product of a bunch of determinants. And this PRC is the square submatrix of P indexed by the rows corresponding to the elements of CR and the columns which lie between these positions. So I'm basically writing the matrix P. One way of computing the determinant, you pick all possible ways of selecting one entry in each row and column, and you multiply and you compute that determinant. That's exactly what we did before. Now I'm picking here, I don't know, C1 corresponds to these rows, and I'm picking this block. C2 corresponds to this row and these rows. I'm gonna come here and pick this block. C3 corresponds to some other rows. I'm picking a bunch of blocks. I'm computing each determinant of these blocks separately, taking the product, and then I will be doing that for all possible ways of partitioning the graph. And it works. It's just a rearrangement of products of numbers. This is called the generalized Laplace expansion of the determinant. Quite nice. Now, the consequence of this is that because the determinant of P is non-zero, okay, there is a feasible partition so that all of these determinants are non-zero. And this is exactly what we wanted. So each one of these blocks appears with their rows and columns scaled in this matrix E sub R. So it is a sort, each one of these little blocks. So this block will be there in the matrix E sub 1 with rows and columns scaled. And this is exactly what we wanted. These determinants are non-zero, so those columns in the matrix, in the projection matrix, will be linearly independent, and therefore we are good to go because of exercise, the exercise here. If the determinant of the block is non-zero, the corresponding columns are linearly independent, and if the columns are linearly independent for all of the parts, then we have a star partition. Now, I know I have not provided a formal proof of this equality, but this is a well-known fact in linear algebra, and this should have been, I mean, if at any point you spend 2 weeks studying determinants, this is for sure a very important expression. Okay, but it's again just a rearrangement of how you compute determinants. All right, and of course, if you're not satisfied with this high-level explanation, you can attempt to prove this by induction. It's not difficult using the formula we had above. Right, the formula equation 2 here, using this formula. All right. So given a star partition of a graph with a spectral decomposition, the choice of the columns is called a star basis. So if this is a star partition, then this columns form a basis for the theta 1 eigenspace, this form a basis for the theta 2 eigenspace, this form a basis for the theta 3 eigenspace, and all of these bases united form a basis for the space. This basis for the space is called a star basis. All right? Oops, what did I do? Come back. Now, what is the interesting thing here now is that we have finitely many possible partitions for a finite set, and therefore we have finitely many possible star bases. Before, I had infinitely many possible bases for each eigenspace, but now I have only finitely many. So I have improved a bit. There are some special bases for each eigenspace which are taken from subsets of columns in the projector matrix. The projector matrix, that is invariant. No matter which U and V you pick, the projection is the same. This is actually quite interesting when you stop to realize that. No matter which orthonormal basis for the space I pick, the projection matrix is an invariant. This is also equal to W transpose plus ZZ transpose if W and Z are a different basis. And when I say equal, I mean equal. It's not similar, it's equal. Okay, the projection acts on the space. So its corresponding matrix is the same. All right. So now you have finitely many candidates And this is going on the right direction. We still have too many though, and eventually the problem is not solvable. But we have finitely many candidates, and this actually goes in the right direction. Okay, so after finding a star permutation, as we did, in section 2.2 in the last class, after finding a star permutation, we proceeded to find a maximal amongst all such, according to a certain ordering. We call that an orthodox star permutation. So following the analogy here, we must determine how to find a maximal star partition. We have finitely many, we want to find the maximal one, somehow according to a certain ordering. So let S be an eigenvector matrix whose columns form a star basis. So now I am picking S to be an eigenvector matrix. Each one of these things is an eigenvector of the graph. Oops. Hold on. Each one of these things is an eigenvector of the graph, and they form a star basis, which means that this first one here are exactly coming from a certain first block in the E sub 1 projection. This second ones here are coming from a certain block in the E sub 2 projection, and so on. So one now looks to these matrices Wi, which are taken from these blocks by performing this. So I take this block here, transpose, I multiply by itself, and I get a square small matrix here. This is called the Gram matrix, oops, of this set of vectors. So if here I have V1 all the way up to Vk, here I have V1 all the way up to Vk, here I have V1 all the way up to Vk, and a given entry here is exactly the inner product Vi, Vj. So this is called the Gram matrix of these vectors. And you can think of this as a symmetric matrix, which is the adjacency matrix of a weighted graph. Now, here's the moment that I will actually stop, and I will not keep discussing the details because they get extremely boring. And frankly, they have an importance, but they do not lead to an efficient algorithm for graph isomorphism. So in a sense, and certainly the algorithm that comes from this is definitely not the most efficient known algorithm for graph isomorphism for graphs with eigenvalues with multiplicity bigger than 1. So I don't think it's worth it, because it's just a lengthy discussion on how to order these matrices and eventually find a lexicographical ordering. Good question, Gabriel. W is not a diagonal matrix because this star basis is not an orthonormal basis. Oops. Nothing here tells you that these vectors are going to be orthonormal, and in fact they typically are not. Okay, so a star basis is not an orthonormal basis. It is though a basis. Okay, Gabriel? Okay, so this is not a diagonal matrix. I mean, if this were somehow a diagonal matrix, graph isomorphism would be polynomially solvable in polynomial time. I mean, if there were a way of finding canonical bases that would result in diagonal matrices here, then life would be sweet. It is possible. I mean, no one knows. Maybe graph isomorphism is solved in polynomial time. Maybe this is the way of finding a polynomial time algorithm for graph isomorphism. Who knows? So basically, it is possible to order these matrices following a certain rule so that one can then search for a star partition whose corresponding sequence of matrices W1 all the way up to Wn is maximal in the lexicographical ordering corresponding to that rule. Such as, so there is a way, I'm not going to describe you the way. Such a star basis will be known as a orthodox star partition. And further, it is possible to now reorder the verses within each class. Also, with respect to the entries of these matrices, once this is done, the corresponding star basis is called an orthodox star basis. What is left from here on is very similar to what we did last class. The rows of orthodox star basis are ordered in the lexicographical ordering, and then matrices obtained in this way are compared in the lexicographical ordering of columns, and then the champion star basis is called a canonical star basis. And believe me, if you perform these processes in the right way, there is only one canonical star basis for a graph. So again, there is a theorem that will tell you that two graphs are isomorphic if and only if they have the same eigenvalues with the same multiplicities and they admit the same canonical star basis built in this manner. So this entire procedure relies on the capability of finding star bases and ordering them. Now, both these things are to be performed simultaneously, exactly like we did before. We had first definition of orthodox permutations, then I told you how to order, but when we were worried about the algorithmic way of performing this, and we actually had to do it simultaneously. We had to somehow go on finding the orthodox permutation that was already a candidate to eventually be the canonical star basis there. Now, both of these things also here must be performed simultaneously, and the main complexity issue of the algorithm is that the most efficient way of ordering weighted matrices as described above relies on computing maximal clicks. And maximal clicks is NP complete. So no. So apart from this, everything else can be carried out in polynomial time, including the task of finding the star basis. Finding a star basis is so before we found a star basis by sort of computing a matching. Here is going to be very similar. So basically the whole thing has to do with how you can order these weighted matrices. This has to do with finding maximal clicks on these weighted graphs, and this is NP hard. Well, finding is NP hard, deciding or whatever, the decision version is NP complete. So, of course, if the sizes of the clicks are bounded, if someone tells you that, and this is exactly connected to the multiplicities of the eigenvalues. So if I say, well, amongst all graphs whose maximum multiplicity of an eigenvalue is, tell me a number, 12. Then graph isomorphism is solvable in polynomial time. Complexity is going to be alpha, is going to be a polynomial of degree 12 or more, but then graph isomorphism is solvable in polynomial time as long as you know that the multiplicities are bounded there. So actually there is a sort of, you guys are taking Vinicius course, so there is a sort of parametrized complexity here. Now, this is not the most efficient way of solving graph isomorphism, all right? In general, but this is a way, and it basically relies on this very complicated yet boring method. And I say yet because some things which are complicated are not boring, but this is actually quite boring. But if you're curious, I can give you I can give you a reference. Now, the thing is so boring that this was once published and in a paper, published and proved in a paper, and the same authors later wrote a book, but they decided not to reproduce the details. So they simply say, roughly, this is what happens. If you want to see the details, go to the paper. But this is well accepted in the community. How does the complexity grows according to the biggest dimension of an eigenspace? So that's what I'm saying. It's going to be a polynomial of degree larger than 12. It has to do with computing maximal cliques, deciding whether or not there is a maximal clique of size 12 in a graph. So you can simply test all vertices of size 12. That's it. So the original paper that showed that graph isomorphism is polynomially time, solvable in polynomial time for graphs with bounded multiplicity did not make any use of star bases at all. It was all relied on the original graph isomorphism routine, which only uses group theory. And that is also on its own very complicated. You need a lot of group theory to understand that. This is more elementary in the sense that you only need to know how to order these things, but it's more combinatorial in a sense, but it's also a mess. Okay? So in case you're interested, you are free to research these on your own. But instead, what I want to focus for the rest of today's class is on star partitions. Okay, so I define star partitions. This is a good question. Ask Vinicius. I don't know. I know the amount of parameterized complexity that I know is what I remember from some talk I watched 2 years ago. So yeah, sorry. So I defined star partitions, and now I want to obtain more information about them. I want to understand the combinatorics of these star partitions. So I do not want to order star partitions, decide which is the biggest, which is the smallest. I am not even too concerned about the problem of finding a star partition. I only know that one exists, and I want to know what else I can say about the combinatorics of a star partition and the rest of the graph. Now, this is a good moment for to stop and give you guys a 5-minute break. We resume at 2 p.m. I'll be right back. If you have any questions, I'll be right back to answer those questions. if you have any questions.
Just for curiosity, do you know the complexity of the fastest algorithm for graph isomorphism?
Oh, it's I know the reference. So this is the reference. So this is exp of log n raised to a constant. All right.
Okay.
So this was a huge breakthrough in 2015. Original submission had a mistake. The second was corrected, and this is a huge result. So this guy is arguably the biggest specialist in the world in this problem. He's been working on this since a long time. The original result for graph isomorphism is polynomial time with bounded multiplicities was due to him and some others. He improved in general, for the general case to this, and then 30 years later, he showed he improved to this one, and this is nowadays the best possible. Now, see, 99 pages, that's a big result. Definitely, I mean, he provided a couple lectures when he proved this first. The lectures are not enough, so it turned into a course. It's a lot of combinatorics and a lot of, I mean, it's basically a graduate course on its own to understand everything that is going on here. Okay, so it's a lot of things. I do not think this algorithm has or will ever be implemented. It probably takes longer to understand this and implement the algorithm than to check by hand whichever graph you want. So,
Sure.
yeah. Yeah. So most graphs are not isomorphic. Most graphs with simple eigenvalues have simple eigenvalues, so you can solve easily. So the graphs that cause problems are graphs with eigenspaces with large multiplicities, which are isomorphic, or which, I mean, everything is similar, but the graphs are not isomorphic. These are quite rare. So most of this work deals with is related on how you deal with these graphs. So these will be these Johnson graphs on the Johnson scheme. This is a sort of a high regular structure with a bunch of graphs with the same eigenvalue multiplicities. So it's all dedicated to deal with the rare cases, right? So that's the so the result is quite nice in terms of what it means, but it's certainly not worth it unless you truly want to research on this field. That's definitely not worth it. Okay.
Okay, but those are some types of graphs which are interesting for algebraic graph theory people.
Yes, yes, yes. So the people that got interested, mostly interested about this result, are the people in algebraic graph theory, not the people working with graph algorithms. Right? Because graph isomorph, I mean, there is a nice question here, which is what is the complexity class of graph isomorphism? I mean, is it a complexity class on its own? Is it eventually solvable in polynomial time? Is it NP hard? Well, certainly if you prove that there is a separation, you're proving that P is different than NP, right? So, I mean, it could be that eventually a proof of that P is different than NP goes by finding something and strictly showing that it's neither, right? Who knows? All right. Star partitions. So we'll start with some very simple yet very useful observation about the eigenvalues of vertex-deleted subgraphs. Actually, this is something quite useful. We will see at least another 2 proofs of this very same fact on this course. And from this moment on, I feel that I'm no longer talking about graph isomorphism. I am starting to introduce the more, let's say, classical spectral graph theory, and my goal is to eventually start worrying about what eigenvalues and eigenvectors have to do with the combinatorics of the graph. Right, so this is no longer, even though I still calling this section 2 in my course notes, this is no longer about graph isomorphism. I'm done with graph isomorphism. Now I want to discuss combinatorics of star partitions. Okay, so we start with this very simple lemma, which says that if you have a graph and a vertex in your graph, and that is an eigenvalue of your graph with multiplicity m, then if you remove the vertex, that is still an eigenvalue with multiplicity at least n minus 1. So of course, if n is 1, it could be that the multiplicity becomes 0 and that is no longer an eigenvalue. But if n is bigger than 1, then you can guarantee that that is still an eigenvalue of the vertex-deleted subgraph, and the multiplicity dropped by at least 1 or dropped by at most 1. It could be that the multiplicity remains the same, and it could be that the multiplicity actually increases. The standard example here is this graph, which is not connected. You're invited to try to find a connected example. The eigenvalues of this graph are 3, 2, minus 1, minus 1, minus 1, minus 1, minus 1. Okay, so 2 minus 1 corresponding to this, and 3 minus 1 corresponding to this. Now, if I delete this vertex, the multiplicity, the eigenvalues are now 2, 2, minus 1, minus 1, minus 1, 1, 2, 3, 4, 5, 1, 2, 3, 4, yes. So upon deleting a vertex, the eigenvalue multiplicity of 2 increased. And that is okay. What we can guarantee is that the eigenvalue multiplicity does not decrease by more than 1. Okay? And a pedestrian way of realizing that is for you to generate a basis for the theta eigenspace for this graph. So theta eigenspace, you write a basis. Let's say our basis goes from V1, this is V1, all the way up to Vm, right? M is the multiplicity. Now let's say A corresponds to the first row of these eigenvectors, right? And what you do now, you assume that the entry here is different than 0, this entry is non-zero. Okay, so simply now use your favorite procedure to find linear combinations of these columns so that all the entries in these other vectors are zero. Simply add a multiple of the first vector to the next. I mean, these are still going to be linearly independent, but you have just now found a eigenbasis for this eigenspace in which only one eigenvector has a entry different than zero. All of the others have a entry equal to zero. Now, it is not, now I want to actually spend a couple minutes here because this is certainly useful in general. So in this course, I will typically say that a vector v belongs to R upper index v. Instead of writing v belongs to Rn. Now this thing is the mathematical notation for the set of all functions f that go from v to R. And in fact, you can always think of a vector as a function that maps elements from a finite set. So this thing here is usually seen as a function that goes from 1 to n to R, which is going to tell you, well, 1 goes to a number, 2 goes to a number, 3 goes to a number, n goes to a number. When you write a vector as a column, you're exactly writing a function that maps the index of this entry to a number, the second to a number, the third to a number, and so on. Now, there's no difference in interpretation if instead of indexing your vectors by 1 to n, you think of it as the things coming from the vertices of the graph. So an eigenvector, or is a function that goes from the vertices of the graph to the real numbers. If v is eigenvector, then AV equals theta v is equivalent to saying that for all a vertex of the graph, theta times VA is equal to the sum over all neighbors of A of VB. This thing here is, you could think of this as a function. The function, right? It's just a different way of writing the same thing. And now, what is happening here? Well, this for all A, I'm simply examining each row of this equation, right? So each row means that I am taking theta times VA on the left, and on the right, I have A times V, which is exactly picking the row that corresponds to A, which has ones only on the neighbors of A, and taking the inner product of that row with the vector V. So I'm summing the entries of V, which correspond to the neighbors of A, which is exactly what we have here, right? If this is still too abstract for you, write an example yourself. Pick the graph P3, write the adjacency matrix, put entries V, VA, VB, VC for the vector V, and see what's going on. Write the multiplication and observe. Okay. Now, so what I'm saying here, now pick one of these guys. Here, right? One of these eigenvectors. So assume V is eigenvector, right? For so exactly as we have here, and assume VA is equal to 0. Now this A here is exactly this A here, okay? Just that it's clear. So what we get is that theta times VA is the sum of the neighbors of VA, VB, and also that for all C vertex of the graph, right, we get theta times VC is C different than A is equal to the sum the neighbor of A, C, sorry, VB. Right? Now, what's happening is VA is 0, so it plays no role in all of these sums. What this means is that for all C vertex of the graph, C different than VA, theta VC is equal to the sum over all B neighbor to C, B different than A of VB. So this now basically tells me that for all C in the graph with A removed, theta VC is equal to the sum B neighbor to C in the graph G with A removed of VB. The conclusion is V is with V with removing the A entry, so V restriction of V to the vertex to this thing minus A is eigenvector of G minus A. Again, this is saying that, right? So this is the right way to think about this. But if you do not like it, you can also think of the matrix product way. It's equivalent. Imagine that this is row A, column A, have a 0 here, a bunch of things, and then here you have the adjacency matrix of G drop A. Right? So this is the adjacency matrix of the graph. This is the vector with a 0 here and something else here. By hypothesis, this is equal to theta times this. But you can also rewrite this product. So there's going to be something here, which is this row times this column. But here is going to be this row times this column, this row, this column, this row, this column, and so on. But all of these entries will be killed by this 0. So this thing here is precisely A of G minus A times V. And this is equal to theta times V. So this is also a way of seeing the same fact. The fact that if you have an eigenvector with a 0 entry, the restriction of that vector to the remaining verses is an eigenvector with the same eigenvalue for the graph with that vertex removed. All right. I think this would work in all cases, Gabriel. I don't see why loops would create a problem here. A loop would simply be an entry different than 0 here. I'm not saying that you can come back. I'm saying if this entry was different than 0, nothing would have changed. Okay, so this is the proof. I have one eigenvector with the A entry different than 0, and I have m minus 1 eigenvectors, linearly independent eigenvectors with the A entry equal to 0, and therefore the multiplicity of theta as an eigenvalue of the vertex deleted subgraph is at least m minus 1. It could be that I also created a new thing from those, as I just showed, but all right, it's quite interesting. So this is one. I proved this right now in two different ways. Right, one is more conceptual, using the eigenfunction interpretation of eigenvectors. Another way is by writing the matrix product on your right, and simply writing the product and seeing restrictions to entries, what's going on. Another way, if you want, which is slightly more high level, is for you to realize that if U is the theta eigenspace and V is the subspace of all vectors with the 8th entry equal to 0, well, you know that U has dimension m, V has dimension n minus 1, and therefore the dimension of their sum is at most n, and the dimension of the sum of subspaces is the sum of the dimensions minus the dimension of the intersection. If you ever saw this, good for you. If not, then the proof is actually quite slightly similar to what we just did. And then as a consequence of this lemma, it follows that, and then as a consequence of this equation, the thing goes through immediately, because this is n minus 1, this is m, so you're good to go, right? You can show that this dimension here, well, satisfies the right value, okay? It must be at least 1. All right. As a consequence of this lemma, it follows that if U is a subset of the vertex set of the graph, and theta is not an eigenvalue of the vertex deleted subgraph obtained from removing U, then U must have at least n vertices. Each one of them, when you remove, the multiplicity decreases by at most 1. If you zero the multiplicity, then you must have removed at least n vertices. Now look at this spectral decomposition again. We say that a partition of the vertex set is a polynomial partition if for each theta r, theta r is not an eigenvalue of G with this vertex set removed. And my goal now is to show that these polynomial partitions are actually the same thing as the star partitions. Okay, so again, what's going on here? You have a set of vertices U. So basically, each one of these guys will be associated to an eigenspace. Right? So basically, theta 1 is eigenvalue multiplicity, say M1, and then you're going there and you get G, you remove V1, and that theta 1 is no longer eigenvalue, which means that V1 has size at least M1. Same thing now, G theta 2, multiplicity M2, you go there, G minus V2, theta 2 is no more, and then V2 has size at least M2, and so on. Now, N, the number of verses, is equal to the sum of the multiplicities. Oh shit, I'm using M twice. Oh no, I didn't want to do that. Let me replace this by, I don't know, K. K1, K1, K2, K2, K1, K2, dot, 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 Kn. Now, each one of these guys is less or equal than the size of V1, size of V2, dot, 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 size of Vm. Now, well, but this guy is also sum to n. It is a partition of the vertex set. Therefore, equality is true here, and therefore equality must be true here. So it really resembles what we were doing before with the star partitions, right? With the fact that we had some linearly independent vectors, vectors generating the eigenspaces, but then they had to actually fit and equality had to be true. It's exactly what's happening here. All right, so a star partition, a polynomial partition is a partition of the vertex set. Each one of these things has size exactly equal to the multiplicity of the eigenspace. And when you remove these vertices, the eigenvalue disappears. Again, the question is, do these partitions exist? And I will show that they exist by showing that these partitions are exactly the star partition. Exactly. So something that is a star partition is a polynomial partition and vice versa. Okay. Now, the lemma 2.10 is actually quite important to verify this fact. It says that a given partition is a star partition. So recall, what is a star partition? You're probably now, I just forgot. What is a star partition? A star partition, so this guy's partitioned the vertex set of the graph, and it is so that the set of E sub r times E sub a for A belonging to VR is basis for theta r eigenspace for all r. So I'm saying that if you find a star partition, you end up showing that if you remove the vertices of each one of these cells, you eliminate the theta r eigenspace entirely. All right, and vice versa. And vice versa. Now, in order to show this, we have this very useful lemma, which says that if you have a star partition, or something is a star partition, if and only if, for each one of the indices, the guys outside of the right subset are orthogonal to the eigenspace. So this is saying that the guys within the right subset, when applied to the projection onto the eigenspace, generate a basis for the eigenspace. So this lemma 2.10 says that it is equivalent to say that if you pick the guys outside of it, they are orthogonal to the eigenspace. It is believable, right? I mean, you have your eigenspaces, they have the right, so, oops. You have your eigenspaces. Let me see how I am going to write that. Let's say you have your theta 1 eigenspace, your theta 2 eigenspace, and so on until your theta m eigenspace. Now, within each one of these spaces, you can find a basis, and the union of these bases is a basis for the space. Now, you also have a bunch of vectors, E sub 1, E sub 2, all the way up to E sub n, right? So this is the canonical basis for the space, the characteristic vectors of the verses, right? So this is 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so on, right? Now, what we know is that a star basis exists, and a star basis is a choice of some of these guys that you will project into the theta 1 eigenspace, and their projections will form a basis for that space. Now, then you go and you pick another subset of these guys, you project onto the theta 2 eigenspace, and they will form a basis for that space, and so on, right? So you partition these guys, you send a couple of them to each one of the eigenspaces, and you're good to go. Now, what this lemma is saying is that alternatively, if this is true, then it must be that when you pick any one of these guys, and you send them to the other eigenspaces, they are zero there. They are orthogonal. So they truly, these guys are somehow only in there. They, with the other ones, they do not interfere, right? So it's sort of believable that something like this would be true, right? And how do we see that? So, yes.
But E sub r, E sub a is the eighth column of E sub r, right?
Right.
But for example, for P4, for every idempotent, the entries are non-zero. So none of the columns are zero there. But you can choose a star partition and
that is actually a good point. That is actually a very good point. This cannot be right. Oh, wow. What am I missing here? Yeah. What did I write on the proof then? Jesus. There must be something wrong here. Terribly wrong. First, assume that this partition is a stop partition. Fix R as the eigenspace as dimension of VR, and these guys are outside. The span of bases of dimension n minus VR. It follows that these spaces are not if they are not orthogonal, then they must intersect. The problem must be here. Like what I can see is that if they intersect, yeah, this is the problem. The sentence is wrong. Hold on. Clearly this makes no sense. May as well just check what I did wrong. The intersection is 0, so that's actually what I wanted to show. Not that they are orthogonal. Yeah, okay, guys. There's clearly something wrong here. It's 5 minutes to the end of the lecture. So let's just stop here. I will fix this, update the corrected class notes, and so this Thursday we will finish this topic. And originally I had planned to talk about power series, but I don't think I will. So I think I will change the class notes a little bit on the website, remove the part about power series, and then move straight to what is now called section 4, okay, which will become section 3. But next class we pick up from here. I will of course fix this. Thank you, Emmanuel. This is clearly incorrect, and I already know what I did wrong. Once this is fixed, there might be a couple of changes on what follows, but everything is okay. And then there will be some stuff here in this 2.7, but then we move to section 4. All right. So tomorrow, as far as or today, is the deadline for the assignment. I will put a very short assignment for this week, only 2 or 3 questions tops. One of these questions that we have we saw today. There's not many things I can ask about graph isomorphism anyway, and that's it. All right, so see you all on Thursday. Bye bye.